Welcome. Today's topic is causal inference. So the idea here is going to be to move past the adage that association does not imply causation and figure out circumstances in which we can draw this conclusion that association does imply causation. So rather than being content with statistical methods that we've developed so far, which are just designed to determine probabilistic relationships between random variables, we're going to develop a framework that allows us to discuss underlying causes as well, so that we can reflect on the relationship between causation and association. So to use this simple example to just have it fresh in our minds why it is that we need something like this, imagine that you work at a company that has an ad budget and records for each month, let's say, how much ad spending it had that month and how much revenue. In making a scatter plot, you see a very strong positive association here. So more ad spending is associated with higher revenue. And based on that, the marketing department might make the pitch that we should increase ad spending so we increase revenue. And setting aside various business criticisms one might have of that position, let's think about the underlying idea that the ad spending is causing the revenue to increase. So problem one asks us, can we think of some other reasons that would induce this association that would not involve a causal relationship? In other words, if we were to increase our ad spending, would the revenue increase? And that might not be the case if this association is due to, for example, both being associated with the holiday season. Alternatively, maybe the cause goes the other way. Management looks at increased revenues and chooses to spend more on ads. In either case, the idea that revenue is driven by ad spending is called into question. So this is a cautionary tale, and it raises the question, how can we draw causal conclusions? So to set this framework up, I want to have a particular scenario in the back of our minds. So imagine that every day you commute from your home to your work, either by train or by car. So this is going to be what's called our treatment variable x, or our input. We decide whether to take the train or the car, and that's going to determine the result we get, whether we're either on time or not. And this is called a treatment variable because often the application domain is medicine, and this treatment variable is going to be, do we administer a drug? 0 if not, and 1 if yes. So in this situation, we'll think of the train as 0, that's kind of the default, and the car as the treatment condition. And then our response variable here is going to be either on time, which will encode as a 0, or late, which will encode as a 1. And the way you probably think of this in real life, you take the train one day and you think, well, what would have happened if I had taken the car? I got to work, I was late. If I had taken the car, would I have been on time? In other words, what you're imagining is that there's some random variable which says, if I take the train, will I be on time? We'll call that C0. And another random variable which says, if I had taken the car, would I be on time? And that one we'll call C1. So these are called counterfactual random variables. The term counterfactual refers to the fact that we'll only ever observe one at a time. For example, if we decide to take the car one day, then the variable C1 determines our y value. We would have y equal to C1 in that case. And then C0 is unknown, which we'll just indicate with an asterisk. Conversely, if we had taken the train, then we get to see C0, that will be our y value, and then C1 will be unknown. So the fundamental random variables here are x and C0, C1. And once x, C0, and C1 are set up, then y is just going to be equal to C0 if x is 0, if we took the train, or C1 if x is 1, in other words, we took the car. And we can combine that into a much more succinct expression by just saying that y is equal to cx. So this is called the consistency equation. Now let's think about what we have in mind when we talk about association and causation in this context. So for example, if we tend to be late when we take the car and we tend to be on time when we take the train, then we would say there's an association between whether we take the car or train and the response y. So the association alpha we'll define to be just the average y that we get conditioned on taking the car minus the average y that we get conditioned on taking the train. So if on average when we take the car we're on time at about the same rate as when we take the train, the association would be 0. The biggest possible association would be if we're always late taking the car and we're always on time taking the train. In terms of cause, though, we're going to want to look directly at the counterfactuals. Every day, if you could see the value of C0 and C1, you could always make the right decision. And even if you just knew the distribution of C0 and C1, you could make the best decision on average. So the average lateness resulting from the car, in other words, the expected value of C1, and the average lateness associated with the train, in other words, the expected value of C0, are really the quantities of interest if you're thinking about causal effect on average. So the expected value of C1 minus expected value of C0 is the average causal effect. And notice that alpha can be computed from the observed data x and y, because it only pertains to x and y, whereas the causal effect theta requires us to think about these counterfactual random variables C1 and C0, and we'll never have complete information in our data about that, because we'll always measure either C0 or C1, but not the other. So in problem 2, we're asked to think about how big the difference between the association and the average causal effect can be. So we're given this table, and we're told that our probability space, omega, consists of the rows of this table. And we're not told in this case the values where the asterisks are. So the probability measure is not fully specified, and we're going to be asked to consider various possibilities for what the asterisks are. The association, however, we can compute without the asterisks. It's the conditional expectation of y given x equals 1 minus the conditional expectation of y given that x equals 0. So we just look where x is equal to 1 at what the values of y are. They're equal to 1 on average. And we also look at the values of y where x is equal to 0, and those are equal to 0 on average. So the association in this case is 1. Meanwhile, the average causal effect, just the average of C1 minus the average of C0. So this is C1 and this is C0. We just average down the column. So the maximum possible theta would be if the expectation of C1 is maximized, which would happen if all of these asterisks are 1. So that's a value of 1, minus the smallest possible value of the average down this column, and that would be if all of these values are 0, and there we would get 0. So you would get a causal effect of 1 at most. So in this case, the association and the causal effect match. And that makes sense if we think about how we would interpret this table. This means that with probability 1, in other words, for every row in the probability space, we would be on time if we took the train, and we would be late if we took the car. So choosing to take the train or the car has everything to do with the result that we get. So this is a scenario which is maximally causal. On the other hand, we can consider the smallest possible theta, which would result if we filled in this second column with zeros and this first column with ones. So now when we take an average of this column, we get a value of 1/2. And when we take an average of this column, we get a value also of 1/2. And so there, the average causal effect would be 0. And that makes sense because in this situation, every day, either we would have been on time no matter what we did, or we would have been late no matter what we did. So in this case, there is no causal relationship between the decision that we make and the outcome that we get. Perhaps when the weather is good, we would have been on time either way, so then we decide to take the train. When the weather is bad, we would have been late no matter what, but perhaps we know that there's less chance we're going to be super late, so we decide to take the car, and we're always late when we take the car. So that would not suggest a recommendation that we take the train rather than the car. So this example is a good indication that alpha and theta are different things, and that theta is capturing some causal information that alpha does not. However, we still don't really have a lead on drawing actual causal conclusions. This is still under the cautionary column. But if we could say that alpha is equal to theta, then we could compute the association from the data and draw causal conclusions about theta from that. And that leads us to the third problem, which asks us to prove the following theorem. If it happens that the treatment variable x is independent of the counterfactual vector, then alpha is equal to theta, which implies that any consistent estimator of alpha is also a consistent estimator of theta. And that means that we can draw causal conclusions based on association. So we're asked to prove this result, and let's just start with theta, which is the expectation of C1 minus the expectation of C0. And think about where we want to end up at the end, which is the expectation of y given that x equals 1 minus the expectation of y given that x equals 0, because that's the definition of alpha. So when you think about what's different, and therefore what needs to change, as we go from one of these expressions to the other, one is that we're conditioning on the values of x, and maybe that's okay because of this independence property. So we'll throw in a conditioning. And then the other is that these c's are turning into y's, and that's going to be okay too because of the consistency equation. So c1 just is equal to y when x is equal to 1. So that should be fine too. So let's just do this step by step. First step is we're going to throw in a conditioning for each of these expectations. And we can do that without changing the value because x is independent of c0, c1. Next, we can replace 1 with x here because we're on the event that x is equal to 1. And the same here, we can replace 0 with x because we know that x is equal to 0. And then we can declare victory because this last step is just the consistency equation. So this theorem gives us our first positive result. If x is independent of the counterfactual variables, then association does imply causation. And the easiest way to ensure this condition is to just assign the treatment condition x randomly. For example, we could flip a coin every day to determine whether to take the car or a train, and then the association value we estimate over time would give us meaningful information about the average differences between lateness for the train and lateness for the car. We eliminate the possibility that there's some other variable z, like the weather, which introduces a non-causal association between x and y. If x is randomly assigned, that's called a randomized control trial. The idea of the term control here being that x equals 0 is the control group. So we're saying the choice of which subjects to be given the control condition is random. And if x is not randomly assigned, this is called an observational study. And it's much more difficult to draw robust conclusions based on observational studies. However, it is important and possible to draw causal conclusions through observational studies, and we know this because of examples like smoking. So definitely no randomized control trial has ever been done where babies are selected in a random way and assigned to be lifetime smokers for purposes of studying their health outcomes. But we can nevertheless be quite confident that smoking does lead to bad health outcomes based on the accumulated evidence of many observational studies. And the key tool that enables causal information to be extracted from observational studies is the idea of controlling for confounding variables. So suppose we're in a situation where x is not independent of c0, c1, but x is conditionally independent of c0, c1 given another random variable z. In this case, z is called a confounding random variable, and we can control for it by splitting up the probability space based on the values of z, computing the association on each part of the probability space separately, and then averaging those associations. And then for the same reason that we just went through in the case where x is independent of c0 and c1, this averaged association, called the adjusted treatment effect, is equal to theta. So adjusting the treatment effect in this way is called controlling for the confounding variable z. It really helps to see this in action, so I've set up an explicit table of values indicating again a probability space consisting of the rows of the table. And here I've fully filled in the counterfactual columns. So in part A, we're asked to compute the association, which is the expected value of y on the event that x is 1, which is going to be 5/6, minus the expected value of y on the event that x is equal to 0, which is going to be 1/6. The average causal effect expectation of c1, so that's the average of this column, which is 9/12, minus the expectation of c0, which is this column, which gives us 3/12. So the association and the causal effect are not equal. However, in part C, we're asked to consider splitting up the probability space based on the value of z. And what we're going to find is that x and c0, c1 are conditionally independent given z. And maybe the easiest way to see that is to think about what the conditional distribution of c0, c1 is given each possible value of x. And since we're also looking at each half of the table separately, we also need a condition on a particular value of z. And what we see is that when x is 0 and z is 0, we have these four possibilities. And the probability measure we're considering on this table is the uniform one, which assigns mass 1/12 to each row. So restricting to these 4 rows, we see that we get half our mass at 0, 0 and half our mass at 0, 1. So we can describe that pictorially with a little graph. C0 on one axis, C1 on the other axis, and we get a 1/2 mass at the origin and a 1/2 mass at 0, 1. Likewise, if we condition on x equals 1, then we get half our mass at 0, 0 and half our mass at 0, 1. In other words, we can say that x is conditionally independent of C0, C1, given that z is equal to 0. Likewise, conditioning on the event that z equals 1 and x equals 0, we get a distribution which has half its mass at 0, 1 and half its mass at 1, 1. And conditioning alternatively on z equals 1 and x equals 1, we get a distribution with half its mass at 0, 1 and half its mass at 1, 1. So either way, conditioning on z equals 0 or z equals 1, we get conditional independence of x and C0, C1. So that implies that we can just simplify this statement to x is conditionally independent of C0, C1 given z. And that means that when we restrict the probability space, just the bottom half of the table or just the top half of the table, then on each piece, we're going to get the causal effect value 1/2. And that's because we can think of each of these table halves as its own probability space, to which our theorem about independence of x and C0, C1 applies and tells us that alpha is equal to theta. So when we compute our association on the top half, we get the average value of y where x is 1, which is 1/2, minus the average value of y where x is 0, which is 0. So we do indeed get 1/2. And alpha bottom, so the association we get when we restrict the probability space to where z is equal to 1, same idea, it's going to be the average value of y where x is 1, which is 1, minus the average value of y where x is 0, which is 1/2. And the adjusted treatment effect we would compute would be 1/2 and 1/2 averaged with weights given by the probabilities of z. So that would be 1/2 for the first one and 1/2 for the second one. And altogether, we would get an adjusted treatment effect of 1/2. Notice that we could have just computed alpha for the top and ignored the bottom, but in practice, we don't want to do that because rather than computing exact values for a probability measure, as we do in this case, the rows will actually correspond to observations from a sample, and so each of these alphas will be an estimate of the alpha for the underlying probability measure, and we'll want to pool those data and take an average to reduce the variance of our estimator. So far, we've been considering 0, 1 valued random variables so that we can list things out in tables and think in really explicit terms about everything that's going on. However, the same basic analysis applies if we have continuous random variables. So instead of just C0 and C1, we're going to have a C of x value for a continuous range of possible x's. And just like in the binary case, we're going to get to observe one of them based on the actual x value that comes out, and the other one we'll never get to see. Similarly, the capital X that you actually realize in the observation leads to a particular point in the final data set, and the whole rest of the curve is never observed. So we get this x, y value contributed to our data set, but then in the next run, C, which is random, just like C0 and C1, might have a totally different shape, and X might be quite different. Maybe this is one instance of C, and maybe the next one happens to look like that, and the X value that gets drawn is here, and so we get another X, Y pair that looks like that. So pretending that we get to know this full counterfactual process is quite a strong assumption in this case. Here we get to see half that information each time, but in the continuous setting we only get to see one point, and we have all of these other points that are thrown away. Nevertheless, if you want to understand cause, for the same reasons as in the binary case, this counterfactual process is a useful tool. So let's look at a particular example that we can plot and start thinking about what's going on. So we suppose z is a uniform random variable between 0 and 10, and u and v are also uniform, let's say between 0 and 1 and -5 to 5. And these are random variables which are independent, and they're going to be providing the randomness that our counterfactual process C is drawing on. So x, which is like the treatment variable, but now it's continuous, so it's the feature variable for our regression. It's just going to look at the value of z and copy it. So x just is equal to z. And then C is going to look at u and v and z and decide what function to be based on what it sees. So if it sees z plus v being bigger than 5, then it's going to take u, whatever its value is, multiply that by x and take the sign and add that to the identity. And if z plus v is less than 5, then it's going to take u, add that to 5, and return the constant function that just says 5 plus u, no matter what x is. So to get a feel for this random process, let's plot several instances of it. So we're just going to follow the instructions exactly. We generate z, u, and v, and then if z plus v is less than 5, we're like, okay, let's return the constant function. which says 5 plus u every time. If it's greater than or equal to 5, let's plot the function x plus sine of u times x. So if we do that on several occasions, we get something like this. So you can see about half the time you get this constant function, which is a little bit above 5. So that's the u adding to 5 to kind of move it up a little bit. And then otherwise you get this thing which is increasing because of the identity function and has this waviness to it because of sine. And the amount of waviness is variable because there's this random coefficient introducing a scale factor there. So if we draw 1,000 observations from the joint distribution on x and y, then we do get something that's different in an important way. So again, we generate u, v, and z, and then we determine x based on that, and we determine y based on that. And then we push to our list of points the new x comma y we came up with. And then we throw all of this randomness, u, v, and z, in the trash. And then we start over at the top, we generate a fresh u, v, and z. So in other words, we're generating one of these graphs from the distribution on C, and then we're recording the x value generated by a capital X, as well as the value of this function at that capital X as a pair, and then we're starting over again. And if you make a scatter plot, you see something that might be a bit surprising at first. So you have this part, which is clearly coming from the x plus sine of u times x part, and you have this thing, which is clearly coming from the 5 plus u part, but you see that there's this pretty drastic tapering at the end. We have very few points right here on the tail end. And that's coming from the fact that in this conditional, z is equal to x, and if x plus v is greater than 5, we're in this first case. So if x is really close to 10, v would have to be really close to -5 over at the left edge of its range of possible values to get z plus v to be less than 5. So that means all the way at the right edge, we're much more likely to be in this first case. And similarly, all the way at the left edge, we're much more likely to be in the second case. So if we were going to compute the regression function, the ordinary regression function, which takes into account the joint distribution of x and y, we would get something that starts out around 5.5, because on this left edge, if we make a vertical slice, we pick up a uniform distribution in this range, and then very little mass down here. So that's going to average out vertically right around the middle of this uniform range. And then as you move to the right, we get more mass below that's pulling it down a bit, but not very much. And then as we move to the right, this starts to contribute less and less, and we get a substantial contribution from this part. And so we're going to see the average value kind of move up. So this is the ordinary regression function, which computes the expected value of y given each value of x. So this regression function is undesirable from a causal point of view, because conditioning on capital X to be equal to little x influences y, in the sense that if capital X is really close to, let's say, this value of x, and we're conditioning on that, then it's much more likely that the counterfactual function was one of these x plus sine of u times x values up here somewhere. And so we get a much larger contribution from here than here. And that's because of the random variable z, which jointly dictates x and the shape of the counterfactual process. Whereas from a causal point of view, what we'd really like to do is take a particular value of x and just camp out there and watch this sequence of c functions go by and just see what values we get. So we get a lot of values here between 5 and 6. We get a lot of values here coming from the x plus sine of u times x function. And then averaging those, we get a value that's maybe like here or something. Similarly, over at this end, we'd get half our values down here and about half our values up there, and in the middle we'd have our average. So overall, the regression function would look something like this from a causal point of view. So again, we're not conditioning on a particular capital X value. We're ignoring capital X, and we're just taking a particular fixed little x, and we're thinking about the randomness in C. What are all the values it could take on? How likely are those values? And we're just computing an average. So we look at the value of C, add our little x, and then just take an average there. So we can see that the causal regression function here is quite different from the regression function computed from the data because of the influence of conditioning on capital X. So we're going to call this causal regression function theta of x. So we can explicitly compute the causal regression function using a bit of probability. So the first thing we're going to do is split the probability space into the part where z plus v is bigger than 5 and the part where z plus v is less than or equal to 5. Then we can replace the expression for c with its appropriate value depending on which part of the probability space we're on. Next, this random variable involves only u, and this one involves only z and v. And z, u, and v were independent. So we can split the expectation across this product to get a product of expectations, and then the expectation of an indicator becomes a probability. Similarly, 5 plus u is independent of the indicator that z plus v is less than or equal to 5. So we get to split that one as well. Z plus v is bigger than 5 with probability a half, and it's less than or equal to 5 with probability a half. So we can evaluate those two expressions. Expectation of 5 plus u is 5 plus expectation of u, which is 5.5, because u is a uniform 0-1 random variable. And lastly, this one we'll just write as an integral and defer to sim pi. So we get a graph that looks like the one that we eyeballed earlier, and we can say in answer to part D, what's the difference between the causal regression function and the regression function? Well, the causal regression function takes both of these contributions seriously, the one coming from the 5 plus u branch and the one coming from the x plus sine of ux branch, even on parts of the interval where x is unlikely to be. And that's because it doesn't refer to the random variable capital X. It just looks at the randomness inherent in the counterfactual process C, so it misses out on the weighting towards one branch or the other that you get from conditioning on an extreme value of x. So adjusting for a confounding random variable in the continuous case works quite similarly. We compute the expected value of y given x and z. So that's our association for a particular x and z value, and then we just weight those based on how likely each z value was to occur. So integrating something against the density of z is the appropriate continuous generalization of averaging it with weights given by the probability mass function of z. And as in the discrete case, if x and the counterfactual process are conditionally independent given z, then we can consistently estimate the causal regression function using a consistent estimator of the regression function. If we're able to estimate the regression function for y given x and z, then we can plug in the z values that we got for those observations in for z, leave x as a variable and take an average, and that's a consistent estimator of the causal regression function theta. And this takes a particularly simple form in the linear case, because there it turns out we can control for z by just including z as an additional feature. So let's see that in the context of a particular example. We're supposing we have 3 independent uniform 0-1 random variables, and x is just equal to the first one, then z is equal to an average of the first one and the second one, and the counterfactual process is just going to be the identity minus 2 times the random variable z plus 0.01 times the third uniform 0-1 random variable. And I'm choosing these small values 0.1 and 0.01 so that we can work this out numerically in a bit and see these values emerging as we're going to calculate them theoretically here. So part A asks us to calculate the regression function given x and z. And that's no big deal because the value for y that we get is expressed in terms of x and z. So if we're conditioning on x and z, we can just substitute those values here, and we're left computing the expectation of uy given this stuff. But uy is independent of x and z, so that leaves us with just the ordinary expectation of uy, which is a half since it's a uniform 0-1 random variable. So we get x minus 2z plus 0.005. The expectation of the causal process, likewise, we can compute by just substituting the expression we got for the causal process and then distributing the expectations. The expectation of z you can work out as 1/2, expectation of uy is a half, and we're left with x minus 0.995 as the causal regression function. Then in part C, we want to show that if r hat is the OLS estimator with features x and z, then what we get when we plug in the observed z's for z, leave x as a variable, and average is a consistent estimator of the causal regression function theta. And the key point here is that the ordinary least squares coefficients are consistent estimators of the actual coefficients if the regression function for the data generating process is actually linear. So because r of x comma z is 1x minus 2z plus 0.005, those are going to be the coefficients. The constant coefficient is 0.005, the coefficient of x is 1, and the coefficient of z is going to be -2. So that's in the limit as the number of observations goes to infinity. Likewise, if we make many observations of random variable z and take an average, then that average is going to converge by the law of large numbers to just the expectation of that random variable, which again is a half. So that means that if we do this thing that we suggested, where we take our estimator, plug in all the values that we observed of z, and take an average, what we're going to get in the limit is beta 0 plus beta 2 times the average of the z's plus beta 1 times x. And that does indeed converge to x minus 0.995, which is the same thing as theta. So in other words, regressing on z as well as x did allow us to recover the causal regression function in this case. In part D, though, we're asked to show, well, what if you didn't include z? Would you maybe still recover the causal regression function? The answer is no. And the key point is that the relationship between y and x is also linear. It just has a different form when z isn't accounted for. So y is equal to x minus 2z plus 0.01 uy. That was just given. And then we can substitute the value for z here. And we can work this out to get that y is equal to minus 0.8x. We have quite a different coefficient here, plus some stuff that involves the u's, which is independent of x. So that's telling us that when we do the ordinary least squares regression with just y and x, we're going to get beta 0 plus beta 1x, where in the limit as the number of observations goes to infinity, beta 1 is going to reflect the coefficient from the underlying relationship, namely negative 0.8. And beta 0 is going to be the average of this other stuff, which is negative 0.095. So here, with the ordinary least squares regression not controlling for z, we don't recover the correct causal relationship. In fact, the coefficient of x even has the wrong sign. So let's take a look at this numerically just to see how it works. Let's define a function which generates x and y and z together. We'll draw 1,000 observations. So these will give us column vectors. Let's transpose them to make them rows, and then vcat them, so vertically concatenate them together. So we get a matrix that looks like this one, and then we can do linear regression just using the linear solve operator. So our feature matrix will have a column of 1s, and then let's consider first just regressing on x. And we get exactly what we thought, negative 0.8 for the coefficient of x and negative 0.95 for the intercept. But if we regress on both x and z, then we get negative 2 for the coefficient of z and 1 for the coefficient of x. So that all worked as anticipated. So again, the punchline there is that for a linear model, you can control for a particular variable just by including it as a regressor in the linear regression. So in summary, the counterfactual model introduces the fundamental variables x, the treatment variable, which is 0 or 1 and specifies the input of the experiment, and two variables called C0 and C1 called the counterfactual variables. And these are meant to indicate the result that you would get had you chosen x equals 0 or x equals 1. The result that you actually get is just whichever C corresponds to the x that you chose. And the equation which ensures that is called the consistency equation. It says that the actual response y is equal to cx, where x is the treatment variable. And the association alpha is equal to the conditional expectation of y given that x equals 1 minus the conditional expectation of y given that x equals 0. In other words, it's the difference in average response on the x equals 1 part of the probability space and the average response on the x equals 0 part of the probability space. The average causal effect ignores the variable x and looks directly at C0 and C1 and just says, on average, what difference in response would I have gotten choosing x equals 1 versus x equals 0? And we learned that if x is independent of C0, C1, then association is equal to average causal effect. And this independence of x and C0 and C1 is typically ensured by random assignment. In other words, we generate x, we determine whether to use x equals 0 or x equals 1 based on some randomness which is manifestly independent of C0 and C1, such as flipping a coin or drawing straws. A study in which random assignment was used is called a randomized control trial, and it supports more robust causal conclusions than an observational study in which x is not randomly assigned, and typically x would not be independent of the counterfactual variables. If x is not independent of C0, C1, but it is conditionally independent of C0, C1, given another random variable z, then z is called a confounder, and we can adjust for z by averaging the association values we compute on each set where z is equal to some particular value. If x is a continuous random variable rather than being a binary random variable, we can just replace the counterfactual vector C0, C1 with the whole counterfactual process, which tells us a c value for each possible value of x. And in that case, the causal regression function, theta of x, is defined to be the expected value of the value of that counterfactual process at x. And the rest of the story carries over quite similarly. We can control for a variable z by computing the conditional expectation given x and z, and then averaging the resulting associations. and if X is conditionally independent of the counterfactual process given Z, then being able to consistently estimate the regression function does allow us to consistently estimate the causal regression function. And lastly, for a linear model, we can control for a variable just by including it in the list of regressors.